Well, hello friends. Today we are going to work on memory size detection. And what I mean by that is that when we look here in the process manager, it says that we have about 67 megabytes of memory available to user space, and then a little bit more, so roughly 70 megabytes. But if you look in the run script, we actually have a RAM size of 128 that we are passing to the QEMU binary on startup. So there's a whole bunch of memory that Serenity does not see or is not aware of. And first, let me show you why that is. So when we create the memory manager, not memory manager object, it's a fix me here. So what we do is we just ask the CMOS object to read out these registers, and there's in the CMOS memory, there's like a memory size field, but I think it seems like it doesn't go past 64 megs or something like that. So that's definitely a problem here. Maybe, oh yeah, it's supposed to actually print this out, ext memory, so let's see, extended mem. Yeah, so see here we find 64 megabytes of that, but that's obviously not enough. So the way that we boot Serenity is that we don't have our own bootloader. There used to be one, but I got rid of it in favor of using this multi-boot thing, which is a standard sort of made by the Grub project, I think, and that's how Grub can boot kernels. And QEMU also supports multi-boot. And what multi-boot does for you, or what Grub does and what QEMU does for you, is that it figures out how much memory the system has and then just passes that information along to you. And then it can also do stuff like setting up a Visa frame buffer and shoveling you the kernel command line arguments and stuff like that. And there's some more stuff in there, I think. But so far, we mostly look at the kernel command line, and we also look at the kernel elf header stuff. But I know that there is some memory map thing in here, the mmap fields. Right. So we have a multi-boot struct here. This is just copied from the spec. Man, my throat is acting up a little bit today, sorry. Got my honey tea here. Yeah, so the memory mapping buffer, I think that's the one. Memory mapping buffer, right. And that's supposed to contain like a table of all of the areas of memory that are available to us, and also the ones that are not available. And those would be like the physical addresses of RAM that we can use, basically. And I think that there's some code here. Yeah, this is actually the one that will just iterate over these fields and then print out each one. So I thought we could just start by copy pasting their sample code and we will see what that looks like. Maybe we'll do it down here right before we call memory manager initialize. Okay, and then Jesus. Seems like this thing is not defined, so we'll have to copy that from the spec as well. So we'll just paste that in here. And we can use the auto formatting thing. There we go. I hooked up Clang format in my editor. It's really sweet. So now I can just press Alt-Shift-F and it gives me it formats the file according to our Clang format spec that we have, which makes everything look just right. Okay, so I think that's it. That's all we need to. Yeah. Right, now we have that, and then MBI here. I guess that's what we would call the multi-boot info putter. Yeah, so that's just what they want, and then we'll use kprintf because we're in the kernel and we have kprintf, not printf. Okay. And we can just try to, maybe we'll hang actually after we print out this information, just because I just want to see what the table looks like. I've never seen it. Okay, so here we are. So this is the memory map that we get from QEMU in this case, but we were getting a similar one from Grub. So these are the base addresses of each range, how long the range is, and then the type of the range, I guess. And I'm guessing the size field here is like the size of this metadata field. So that's probably just relevant for iterating through the table. Right, so what are those types? There were some defines. So we have types 1 and 2 and 1 and 2. Those are available and reserved. Well, that's straightforward enough. So I suppose the ones that we care about are the available ones. Okay. Now, what we do here, we have a function called memory manager initialize paging, and in the constructor of memory manager, that's what we'll call. And in initialize paging, we then just iterate here. This is very hackish, so we're just iterating up to the starting from the 4 megabyte mark to the RAM size mark, which was the way that we currently do things, and clearly is not the right way to do things. And then for each page, we just create a physical page, a little wrapper object, and put that into the free physical pages list. What does this object look like? Physical page has a retain count, may return to free list, is it a supervisor page, and the address of it. And there are definitely more clever ways to store this information. Like, I don't think we would even need to have a separate object for free pages. They could just be like stored in the physical page somehow, like as a linked list or whatever. But right now, we have a physical page for every physical page. Physical page object for a physical page. So we're just going to keep it that way because it's simpler, but in the future we can definitely come here and tighten this up with some much more efficient allocation strategy, or free list strategy. Strategy, I guess I should call it format. Anyways, so what we want to do now is for each of these available pages, so that's type 1, we want to just iterate over this range and create a physical page object for each one, I think. And what is that? Okay, this is very early here. I just got out of bed, so I have to cheat and convert that to a megabyte for me because I can't do hexadecimal yet today. Okay, so at the 1 megabyte mark, going all the way up to here, we have available memory, right? And then below the 1 megabyte mark, it's a little murky. Most of the memory is available. But I think that we should leave it alone, basically. And we can start carrying at the 1 megabyte mark. So let's see what we would do. So let's take that code and bring it with us to the memory manager. And let's see. I guess we can say like, we should include multi-boot session, kernel, multi-boot. Let's sort those. Frickin' throat. Okay. Oh wow. I didn't actually look at this code that I was pasting, but it's really quite hideous. Ugh. Look at all that stuff happening in this for loop. Okay, just so that I can read what the heck is happening here. Okay. Oh, thank you, Clang format. So I guess we should just do this iteration thing, but we are just going to care about these available ones. So let's see. We'll say that if a map type is not multi-boot memory available, continue. And oh god, this is so gross. Why does it span so many lines? Okay, I'm just gonna do auto star here, and then we can get rid of this one. And yeah, that's fine for now. Okay, and then we skip over those, and then we can also skip over adder is less than the 1 megabyte mark. Then let's just skip over it for now. Fix me, maybe care about that. Maybe make use of stuff below the 1 MB mark. Okay, so now we know that we are above the 1 megabyte mark, and we are an available segment, or whatever you want to call this. Whatever you want to call this thing. Okay, and then we can do something like size t as I, a map adder, I is less than a map adder plus a map size. And I plus equals page size. And then we will just create physical pages for this. Oh, right, but for the 4 megabyte mark. Okay, right, so if it's below the 4 megabyte mark, then we will make supervisor pages, and if it's above the 4 megabyte mark, then we'll make, oh, I'm forgetting about something. Right, so kmalloc is using the 1 megabyte through the 2 megabyte space for internal, and then 2 megabyte through 3 megabyte space for kmalloc. Kmalloc internal is it's a variant of kmalloc that is guaranteed that you're never going to free that memory, so it's for like objects that never go away, and because of that, they can just be allocated like really tightly packed without having to maintain any metadata that you would need for free. And then kmalloc is a regular heap allocator. And then 3 megabyte through 4 megabyte, that's dedicated supervisor physical pages section. That's for stuff like page tables and just pages used by the kernel. And maybe we should have more than 1 megabyte for that, but currently that's what we have. So what we need to do here is we cannot care about anything below the 3 megabyte mark, actually. So, but that will be here. So if I is a really bad name here, actually. So I'll rename this to page space. if page space is less than 3 megabyte mark, then continue. Okay, and then if it's less than the 4 megabyte mark, then we'll say m3 supervisor physical pages and physical page create eternal. That's this type of eternal object that I was just talking about. Physical address page base and true because it's supervisor page. Okay, and then else m3 physical pages because then it's just a regular physical page. Create eternal physical address I, and it's not a supervisor page. No, it's not I, it's page base. And we can just not do this. And then we don't need this code. And then, I guess we don't need that code either. Oh geez, how is this gonna work? Let's just try it. Assertion failed. Right. No physical pages available. Well, let's see what we can do here. So let's just print out the page space that we are trying to do, because maybe we don't never even get here actually. Page space. Now we do one of them. Oh shit! Wait, hold on. We do get here, but then we skip over it to continue. Page space is less than mmap adder plus mmap size. Oh, because it was size was the one I didn't want. It was the len. And I guess these are actually these are 64-bit values, but right now we're at a 32-bit operating system, so it doesn't really matter. But whenever we make this into a 64-bit operating system, we're gonna have to go here and care, but there's gonna be a whole lot of stuff to care about, so let's not worry about that right now. Okay, so it looks like we are instantiating a whole bunch of those. So many, in fact, that we run out of space in the eternal allocator. That's pretty funny. Okay. So the eternal allocator only has 1 megabyte of space. It seems like we wanted to create a whole lot of objects, and it's this type of object, and it's what, 8 bytes? Oof, I can't even. How many of them did we want to make? Let me count these. Let's just say C, size to C. Now I'm curious, how many do we need? Hmm, 32,000 of them. How much is that times 8? It's not that many. Why are we running out of space? Okay, malloc eternal. Plus equals size. I would have expected us to fit more in the eternal allocator. Let's print out here how much we have eternally allocated. This is the whole eternal allocator, by the way. It just bumps a pointer. Let's see, so that would be U. Blah, blah, blah. Come on and die. Oh. Oh, we die afterwards. Oh, we didn't die during that part. So we were just filling that up. And then we were eternally allocating something else. Seems to get way bigger. What are those things actually? I don't know. Let's find out what they are. So this is the allocation stack. It's hex only because this is before we've loaded the kernel symbols. Then you only get stacks that look like this. So oops, that's not what I wanted. Dump 19A7B. Yeah, assertion failed. Sure, I can tell that much. 1995. Malloc eternal. Sure. 2VDEF. That's where we're calling it from, I guess. Where are you? Load K. So we're loading the K-sims. Okay. Load K-sims. So loading the K-sim or the kernel symbols is probably what's killing us. Yeah, so we're right here. No, we're not right here. This is the big table of K-sims, and down here is each individual K-sim. So it seems like we don't have space. How big is the K-symbol thing? Kernel map. 204,000 bytes. Well, I guess we can't fit that. That's unfortunate, but it is what it is. If that doesn't work, I guess we should think about this somehow differently then. Maybe this thing I was saying about having a free list for the pages is something that we should do right away, but I would like to do that separately. So let's just solve this with some engineering instead. Some let's see how we can get rid of this problem. So the issue is that we are creating all of these and they take up so much space. Can we make them smaller, I wonder? I guess we could make them half the size. We could like pack all of this stuff into the bottom part of the address. We could say like if the address is below the 1 megabyte mark, then all of it is just metadata instead. Or like then that would mean that it's a free entry. But no, that doesn't really work. Or at least that doesn't work the way I wanted it to, so forget about that. We could make more space in the eternal allocator. So we could say that the eternal allocator goes, I guess we could say that it starts at 1 megabyte, but goes all the way up to 3 megabytes. And then kmalloc would start at 3 megabytes and go to 4, and then we would just nudge this whole thing a little bit. It's a bit ugly, but we can do that. So we'll change our map to look like this, I guess. Like that. Wait, what am I trying to do here? No, that's what I wanted to do, right? And then, yeah, and then in kmalloc, we would do something like, say the eternal base physical starts at here, but then it would be this big instead. I wish these would be more readable, so let's just say 2 MB, 1 MB, base physical. Right, so the kmalloc now starts at, wait, fuck, I already forgot what it looked like. Kmalloc starts at 3, goes to 4, right? So it starts at 3 and it's 1 megabyte large. Okay, this is very hackish. But we should have 2 megabytes of that stuff. But now something else is going wrong. So what am I screwing up? Goes from 1 to 3 and then it goes from 3 to 4. That's probably fine. So I'm just messing something up here. If it's less than 5, then it's a supervisor page. Else it's a regular page. Okay, let's just try that again. I'm wondering if I have some hard-coded memory stuff elsewhere that I'm forgetting about. So we definitely don't care about this RAM size business anymore. We're using that anywhere. No, we should just get rid of this because it's not canonical anyway. RAM size. Yeah, okay. We'll just make sure that everything is purged of that old stuff. This is the page tables, and here are some hard-coded addresses well below the 1 megabyte mark, apparently, but they shouldn't bother us right now. Okay, so why search and failed current? So we're getting a page fault. Exception 14 is a page fault, and we don't have a current thread. So that just means that we're not used to getting page faults before there is a current thread. So something is going wrong, obviously. And what is that? Probably I'm allocating something that... oh wait, I do this identity map thing. The bottom 4 megabytes, except for the null page, are identity mapped. Yeah, right, so we need to identity map the bottom 5 megabytes. Instead of the bottom 4. No? Wait, what? Oh, wait, hold on. Because 4 megabytes, that's one page directory entry can hold 4 megabytes, but since I'm expanding this to 5, then it's going to fail, or one page table rather, it's going to fail to allocate a page table. So we're going to need, it's just hard code, page table 1. Where do we put this code? This is a bit ugly, but let's just power through. Okay, so the thing is that page tables are dynamically allocated, but since we need to access the memory between 4 and 5 megabytes before we have anything populating the dynamic page table allocator, we have to manually allocate a, oops, what the heck am I doing? Manually allocate a page table for that. address range. There we go. Okay, so if the page directory index is 1, then I'll use page table 1, which is then hard-coded at this address. It's ugly, but hopefully that would work. Build faster. Just build faster. Okay. Well, we made it a little further. What's your problem now? Can't write to this virtual address. All right, and we are here. And let's just look what that code is. We are in allocate supervisor physical page. Well, that's goofy. So allocate supervisor physical page. And we are in a rep stas, so that looks like an inlined zero fill, which is probably this. So we allocated a supervisor physical page, and we probably got exactly this address, which is at the end of the 4 megabyte, between 4 and 5 megabyte range there. We're trying to zero fill it, and it just does not work out because we get a page fault. Let me see if I screwed that up in some obvious way. I'm zero filling the page tables. I'm initializing it like that. And oh, hold on. I need to populate page structure. So all the child processes, or all processes, need to have the global kernel page directory entries. So it's the page table 0 and page table 1. They both need to be available in every process. Otherwise, that's just going to fall apart. Okay. There we go. Cool. Let's see how much memory we have. Look at that. 131,000 Ks. Very nice. I wonder, let's try to allocate a bunch of it. Maybe we will run a kernel heap before anything else. Look at that kernel heap pushing up against. Against the 1 megabyte mark there, but I guess we can make the window bigger, because that should only grow the user space memory usage. Oh, look at it go, 64. Wow. System is starting to get a little sluggish. I guess because I'm drawing a humongous bitmap all the time, but we are still going. Wow, I've never used this much memory before. Oh, look. We're gonna run out of pages. Come on. Come on, dude. Oh, here we go. Fuck! No physical pages available. Okay, well, that's pretty cool. We managed to actually use the 128 megabytes. Of course, we should probably do a lot of nicer things when we start to run out of memory, but right now the system will just panic and die. But you can't solve every problem immediately. So let's just make a quick scan here just to see if we can get rid of something, or that I'm just forgetting something obvious. No. Okay, so let's think about what we're doing here. So currently what we've done is we've changed the memory map so that we gave KMalloc Eternal an additional megabyte of space, which is really just, we're just like papering over the problem that we run out of eternal memory. So it came like eternal memory. So that we can allocate all of those physical page objects that represent each physical page. Of course, if I run QEMU with like a gigabyte of memory, we are gonna exhaust the K-malloc eternal heap once again. So this is not a sustainable solution. We need to solve this in some other way, but it will work right now. Can't solve everything in one patch. And then, so we just rejigged or like rearranged a little bit here. Or really we just fattened up this guy and then moved everyone else. And because we moved the supervisor physical pages, we moved them outside of the initial 4 megabytes, then that forced us to create an extra hard-coded page table. Page table 1. Because page table 0 has all the mappings for the first 4 megabytes, and then page table 1 has all the mappings for the next 4 megabytes, and so on. Okay, so we can skip printing that. We don't have to print that. Yes, I think that's cool. We don't have to print these. And we can just put multi-boot info footer directly. And geez, this is so ugly, but let's just keep that for now. And I know that this thing here is not super robust because like you could have information coming from the bootloader that doesn't exactly look like this layout, and it will fall apart a little bit. But for now, this works, and then we can do this again for. We're gonna have to work on this anyway. So I guess that's my point. But we should probably have this information here that we're printing. So let's see, multi-boot mmap. We can say something like that. Multi-boot mmap. We'll call these D words. Oops. Maybe, oops. Oopsie. That's pretty good. Okay. Oh shit, I'm not actually gonna print all of them. Okay. There we go. Otherwise we would skip over some, so this way we get to see all of them. Just verify that everything comes out the way that we would like. Multi-boot mmap, yeah. So those are all the things that we wanted to see. Cool. I think maybe we don't care about this field actually, so I'll just leave that alone. Yeah. Okay, so let's do a patch review. Right, so first we are just taking in that struct definition and the macros from the multi-boot spec, and then including multi-boot H in memory manager. And then we get rid of the old way of detecting the memory size. Then we add the hard-coded page table 1, making sure that every new page directory gets that mapping, the page table 1 in addition to the page table 0. And then we make sure that we clear out page table 1 on startup. Okay, and then when we create identity mappings, I see that we have an out-of-date comment here already. I don't like these. I don't like that these comments are so repetitive because they fall out of sync, or they fall out of sync very easily. But we don't have to fix that right now. Okay. The bottom 5 megabytes are now identity mapped. Identity map means that the virtual address maps to the same exact physical address. So like the virtual address 1 megabyte maps to the physical address 1 megabyte. That's identity mapping. And we do that for the bottom 5 megabytes because it simplifies the way that the kernel is written, because then you know that, like, if you have a pointer, then the pointer value, any kernel pointer value is like the same as its physical address. You never have to wonder about that. Okay. And then we just update this map here, and instead of just iterating from 2 to 4, oh, this is so weird. I think this wasn't even right before, actually, because we were iterating from 2 to 4 and creating supervisor physical pages for each one, but our map said that 2 to 3 was kmalloc space. So allocation is backwards. So probably we had a bug here, actually, that if you would keep allocating enough supervisor pages, you would eventually start to steal kmalloc pages, and you would run into all kinds of horrible bugs. So probably an unintentional bug fix here, so yay us. Okay. Now we iterate over the multi-boot memory map, and we just print them out, blah, blah, blah. We print out each one, but then if it's not available, then we skip over it. If it's below the 1 megabyte mark, we skip over it. And then we iterate over the map, or the table mapping thingy, or the segment, 1 page size at a time. And if we're below 4 megabytes, then we don't do shit. Maybe we should explain that. If this page is managed by kmalloc, skip. I wish to skip over pages managed by kmalloc. Yeah. Maybe we should put it like this so that we can sort of scope the comment a little bit. Okay. Right, so now for anything between 4 and 5 megabytes goes in the free supervisor physical pages list. Anything above 5 megabyte goes in the free physical pages list. Cool. And then we just get rid of the old way of doing things. And here is when we ask for the page table entry for page directory index 1, then we now just use our hard-coded page table 1 rather than allocating one dynamically. Okay, then we get rid of the RAM size getter, add the page table 1 thingy, and I don't like that they look so naked here, so I'm just going to initialize them with null putters. Just, I find that that's a good habit. Okay, and then finally, in kmalloc, we update the eternal range to span 2 megabytes rather than 1 megabyte. And because of that, we have to move the base of the regular kmalloc to go start at 3 megabytes. Cool, I think that's a commit. So, kernel. Use the memory map info from multi-boot. Let's put here multi-boot memory map info to inform paging setup. Inform our paging setup. No, possible, or this makes it possible. Trinity with more than 64 megabyte of RAM. Because each physical page is represented by a physical page object, and those and such objects are allocated using kmalloc internal. More RAM means less, more pressure on internal. So definitely we're better strategy for this. For now, let's just celebrate that we can use the RAM we've been telling QEMU to run with. Cool. All right, let's see that again. Look at it. So much memory. Very nice. Oh, let me see what it looks like in this graph. I should probably have some way to pressure test the memory, but this works pretty well. I mean, that's a stupid manual test just to see that the graph keeps going up. It's very cool. So I think that's going to be it for this video. I'm happy that we didn't crash and burn and end up in a total swamp of not being able to figure this out, because it turns out it was pretty straightforward, actually. So if you made it this far, then I thank you for watching and for coming back and hanging out while I hack. And I will see you next time.